Hello everyone, I am Natasha Singh and welcome to this presentation on finite automata in search engines. Today we're going to explore on how a concept from theory of computation, something that seems very mathematical and abstract, is actually used in real world systems like Google search. By the end of this video, you'll clearly understand not just what finite automata are, but also how they power features like autocomplete, spell checking, and fast search results. Let's start with the foundation theory of computation. This is a branch of computer science that studies abstract machines and problems they can solve. It helps us answer very fundamental questions like what can a computer solve, how efficiently can it solve it, and what are its limitations. Even though it sounds theoretical, it has a massive real world impact. For examples, compilers use these concepts to understand code. Search engines use them for pattern matching. Artificial intelligence systems rely on structured computation models. So, what we're studying here is not just theory, it directly powers modern technology. Now, let's focus on finite automata. A finite automaton is a mathematical model used to recognize patterns in input strings. Think of it as a machine that reads input one symbol at a time, moves between different states, and finally decides whether the input is valid or not. There are two main types of finite automata, namely DFA, which means deterministic finite automata. In that, there is only one possible transition for each input, uh, making it very predictable and easy to implement. Secondly, NFA, which stands for non-deterministic finite automata. There are multiple possible transitions in this automata, and it is more flexible, but it is not directly used in real systems. In practice, NFAs are converted into DFAs for efficiency. Now, FA components. Every finite automaton is built using five core components. First, we have states, which represent different stages of computation. Then comes the alphabet, which is the set of input symbols like 0 and 1 for binary settings, uh, binary strings. Then comes the alphabet, which is the set of input symbols. Then comes the transition function. It defines how the automaton moves from one state to another based on input. The start state is where computation begins, and finally, the accept state or the final state, which determines whether the input string is valid. So essentially, the automaton reads input step by step and transitions through states until it either accepts or rejects the string. Now, let's understand this with a concrete example. This DFA that we can see here, it accepts binary strings that end with 0, 1. Now we have three states, which is Q0, that is the start state, Q1, which is the intermediate state, and Q2, which is the accept or the final state. Now, we'll take an example of input, which is 1101. Let's go step by step. At start state, which is Q naught, we if we get the input one, and if the state it reads the input one, it will move to Q1. Again, if it gets Q1, if it gets input one again when it's in Q1 state, it will stay in the Q1 state. But if instead of 1 it gets an input of 0 when it's in state q1, then it will move to the next state, which is q2. And if it reads q1, then it moves to the final state q2 again. Since we end in the final state or the accept state, the string means the that means the string is accepted. So this DFA is essentially tracking the last two bits of the input. Now, finite automata are extremely important because they are built specifically for pattern recognition. They process input in a single pass, which means the time complexity is linear. This makes them very efficient even when dealing with large data sets. That's why they are used widely in compilers, search engines, network protocols, basically anywhere pattern matching is needed. Now let's connect this to search engines. When you type something in Google, a lot happens in the background. The process usually follows these steps. In firstly, input query, then it goes to tokenization, then it goes to pattern matching, and then in the end, ranking and results. The system processes millions of query per second, so efficiency is critical. This is exactly where Automata comes into the play. Finite automata are used in multiple parts of the search engine. In query matching, they compare user input with the stored data. In text scanning, they process large data sets efficiently. And in pattern recognition, they detect keywords and structured patterns. This allows search engine to quickly find relevant results from billions of documents. Now, let's talk about autocomplete, something we all use daily. Now, you start typing something like Google. Suggestions immediately appear. The key idea here is prefix matching, which Automata handles very efficiently. If you like this example here, you can see when we write Google, automatically there are many suggestions that the Google search engine gives us, which is Google Maps, classrooms, documents. This is also based on the ML is basically trained to recognize patterns. Like it must have had the history of people. Usually, when they type Google, what is the next word they usually use. So the according to that pattern, it uses that pattern matching. The automata uses the pattern matching to help in autocomplete function. In autocomplete systems, each state represents a prefix. For example, here F and then FI and then FIN. Each transition adds a character. The system uses a data structure called try, which stores words in a tree format. The automata traverses this structure to generate suggestions quickly, which is why suggestions appear instantly as we type. Regular expressions are patterns used to match text. For example, we can define patterns for emails, for phone numbers, or just keywords. These regex patterns are converted into automata. Regex is converted to NFA, and then NFA is converted to DFA. This conversion allows systems to efficiently search through large amounts of text, just like Google searches through billions of documents and billions of links that it holds to give us the relevant information. To give us the relevant site that would be required, like whatever site that comes up with that keyword that we've inputted in the search bar. Now, moving on to the next slide, let us now let's look at the query process flow, the whole complete pipeline again. The user enters a query, it is broken into tokens. Each token is processed by an automaton, then pattern matching is performed. Finally, results are ranked and displayed. The entire process happens in milliseconds. Advantages of using Automata. Automata provides several advantages. They are fast because they process input in linear time. They are memory efficient since they only track the current state because it works on the current state. They are scalable, handling millions of queries, and they are predictable, giving consistent results. Now, coming to the limitations of finite automata. Uh, it does have limitations. They cannot handle complex structures like nested patterns. They also have no memory beyond the current state, which again is because they only work on the current state. They cannot track long dependencies. For more complex tasks, we need models like push-down automata or the Turing machines. Moving forward to the advanced concepts, in real system, automata are optimized further. NFA is converted to DFA for efficiency. DFA is minimized. DFA minimization is done, which reduces the number of states. Tries are combined with automata for autocomplete. And algorithms like Aho Korasik allow matching multiple patterns at once. These techniques